And this curve that is shown is for a pump with a 12-inch impeller that's operating at 1,000 RPMs. What would the capacity, head, and power of a similar pump with an 8-inch impeller that operates at 1,200 RPM be? So as we're taking a look at this, we're going to match up those coefficients of capacity, head, and power to figure out what the new capacity, head, and power is going to be. First thing that we need to do is we need to take a look at this, and we need to know what is my capacity, head, and power for that first pump. So I have the curve so I can calculate it out. So remember, the thing is this stuff is usually evaluated at the best efficiency point. So as I look at it, the best efficiency seems to be right here. Ooh, that's mostly straight line. So right here is where I'm peaking out efficiency. There's where my head is. There's where my horsepower rating is. And so it looks like that is all going to occur for the first pump at 3,000 GPM. So as I look at my head, here's my head curve over here. If I read over to the side here, we're going to assume that our head is sitting there at 66 feet from the curve. And then I look at my brake horsepower. My brake horsepower is right over there. And so we will assume 55 horsepower. So now as I'm looking at this, I know that my impeller diameter is given to me in the problem. So my diameter of 1 is going to be 12 inches. And I know my RPMs at 1 are 1,000 RPM. So that's all what I know for the first pump. Second pump, I know that the diameter is going to be 8-inch. And I know the impeller speed is only going to be, is going to be 1,200. It's actually faster, not slower. So what do I do? Well, I'm going to match up my dimensionless parameters. So CQ1 is equal to CQ2. So as I look at that, what does that tell me? That's Q n d cubed at 1 is equal to Q n d cubed at 2. Now I could go convert this all into a dimensionless friendly form, calculate out exactly what the dimensionless parameter is, match it to the other one, and then convert it back and do all that. But if I look at things here, I can actually do this a little bit simpler. So I'm trying to find Q2 because I know everything else on this problem I know. So let's rearrange this for Q2 because that's what we're trying to find. So Q2 is going to be Q1. And then we're going to multiply it by N2 over N1. And then we're going to multiply it by D2 over D1. All of that raised to the third. Now, as I look at this, what's going to happen? N2 and N1 are both in RPM. They're going to cancel out. It's not going to matter. D2 and D1 are both in inches. Going to cancel out. It's not going to matter. The only unit I'm going to be left with is the unit of Q1, which is going to be in GPM, which is what we're trying to get out of the problem anyway. So when we're doing it like this, we really don't have to worry so much about getting the units to where they'll be dimensionless. We just need to make sure the units are the same for each problem. So in this case, we're trying to find out what that second flow rate's going to be. It's 3,000 GPM. Now I know that both of these numbers are going to be in RPM, so I'm not even going to write the units because they're just going to cancel out. And I know they're the exact same. Same here, 8 inches, 12 inches, and I'm going to cube that. So I'm going to calculate that out, and what I'm going to get is that if I take that pump, I make that impeller a little bit smaller and spin it a little bit faster, I'm only going to be moving 1,067 GPM instead of moving the 3,000 GPM the initial pump does. So now I'm going to do the same thing for my coefficient of head. Now, my coefficient of head does have that gravity term into it. So coefficient of head 1 equals coefficient of head 2. And that coefficient of head 1, GH, divided by n squared d squared, all of this of 1, has to equal all of this of 2. So our gravity is not changing. We're keeping this pump on Earth. We're not taking it any place, not putting it on a space station or anything. they could be, but they didn't tell us that in the problem. So I'm pretty confident in going, my gravities are the same. So the gravities will cancel out. Makes my problem a little bit easier. So I rearrange this equation. I'm going to get H2 as H1. They're both going to have units of feet. And then N2 over N1 squared, D2 over D1 squared. Oops. And I have my entire world changed on me. So now if I plug the numbers in, 66 feet is my head. N2 over N1 is still 1,200 over 1,000 squared. And then 8 over 12 squared. So if I calculate that out, I bash those numbers. The only units I have left are feet. So I get 42.2 feet. Actually, let's box these because they are the answers. So I'm running a third of the flow rate, but I'm getting 2/3 of the head. That's not too bad. It's an interesting little pump. So let's go now and let's look at our last one, and that's going to be our coefficient of power. Coefficient of power at 1 is going to be the same thing at 2. So the brake horsepower divided by rho n cubed d to the 5th at 1 is going to be equal to all this at 2. Now, just once again, this is where it gets interesting if you're using a different fluid because you have those densities in there. And you could be running the same pump at the same flow rate, and just by changing the density out, we'll be able to tell you how much quicker, or excuse me, how much more power that you're going to be using. So our densities are going to cancel out because we are using a water pump. So if I do that and I rearrange this for BHP2, it's BHP1, N1 over, excuse me, that's N2 over N1, all that raised to the 3rd, D2 over D1, raise that to the 5th, and that's going to be 55 horsepower, 1,200 divided by 1,000, raised to the 3rd, 8 divided by 12, raised to the 5th. That's going to give us 12.5 horsepower. So not a bad little pump, using a lot less energy, a lot less flow rate, but still providing a very good head based off that.